What's up, everybody? Welcome to Lecture 3 of our Bonding CPS lecture series, I guess, or whatever you want to call this. In this one, we are going to be talking about writing and naming those ionic compounds that we talked about in the last one, but I want to get done with this quick, and you don't want to be here all day, so let's skedaddle. First thing I want to talk about is binary ionic compounds. Binary ionic compounds has that word binary in it, right? That prefix of bi. Well, a binary compound is a compound that has two different elements in it and only two different elements. That's the big thing from this. So before we can write the formula, we have to make sure we know what's in it. We need to know what elements are involved, how many elements total are in the compound. Is it a binary compound, or is it something that's not binary, which would have more than two elements? And we also kind of need to know what's going on in the losing and gaining of electrons. Yeah, it also says sharing, but sharing is a type of bond called covalent bond, and that is something we'll do later on. Well, one of the most important things is knowing the number of electrons that an element gains or loses. We would call this the oxidation number. All right, and for ionic compounds, oxidation number is the same as the charge of the ion. In fact, I like to say oxidation number is the fancy chemistry term for charge of an ion in ionic compounds, right? Now, way past ionic compounds, later on in chemistry, you might get better definitions of oxidation number that are more complete, but in a class like this, or this situation, let's try to use charge and oxidation number as pretty much synonyms. The oxidation numbers are pretty easy to find on the periodic table. If I look at the far left and far right of the table, the different rows, or not rows, the different columns have the same oxidation number. The first column tends to always form +1 ions, or 1 plus ions. The second column, 2 plus. And then if you skip that chunk in the middle, all right, group number 13 plus 3, group number 14, 4 plus, and then after that they start to form negative ions. Group 15 is 3 minus 16, 2 minus, and 17 is 1 minus. Group 18 doesn't usually have oxidation numbers. This is a handy little thing to kind of keep near you for when you are doing these. So make sure you somehow get a picture of this slide or something, because you're going to want to be able to refer to it going forward. Now, we skipped over a huge chunk of elements in the middle. Those are known as the transition metals. Those transition metals have multiple oxidation numbers, more than one possible oxidation number. Some have as many as 7. We're only going to look at a few special ones, all right? In fact, we're going to take a look at 8 special ions. They come in pairs of 2. There's copper, iron, chromium, and lead. These are the ones we're going to look at. And you can see copper can be 1 plus or 2 plus, iron can be 2 plus or 3 plus, chromium 2 plus or 3 plus, and lead 2 plus or 4 plus. Now, this is not by any means all of these that are out there, but it is a good big chunk of them. And what you will notice is you'll notice these Roman numerals here. Notice copper 1 plus has a Roman numeral 1. Copper 2 plus has a Roman numeral 2. Iron 3 plus has a Roman numeral 3. This Roman numeral tells you the charge, tells you the oxidation number. And these are only for metals, and they're always positive. We don't use these for negatives. For negative oxidation numbers. All right. Only for positives. And so I would try to make sure this chart is available somewhere in case you need to refer to it as well. Then, we could have a situation where we have compounds that are not binary. Not all compounds are binary. There are some that have more complex ions. We call these complex ions polyatomic ions. All right? And a polyatomic ion is negatively or positively charged. Most of the time it's negatively. It's a group of atoms. All right? And if I take a look at baking soda, I know I'm kind of jumping around on this page, but baking soda is NaHCO3. Right? There's sodium, hydrogen, carbon, and oxygen in there. There's 4 elements in baking soda. That means it's not binary because 4 is not 2. All right? So somewhere in here there's a polyatomic ion, a many atom ion. All right? Again, there are hundreds of these out there, but we're only going to worry about a select few. Those select few polyatomic ions, the ones that we will say are common polyatomic ions, can be found on this table, on this page, with their charges. All right, notice most of them have negative charges. All right, and that is the case. The one difference, the one little adjustment to this that I would make is I would take these and I would put them in parentheses. All right, leave the charge on the outside. The entire grouping of elements in the polyatomic ion stays together. All right, and I would just put them in parentheses like that as a way to show that they stay together. All right, as you see, most of them are negative. All right, there is the one fancy positive one, ammonium, which is NH4 with a 1+ charge. And if you look at a lot of the negative ones, a lot of those negative ones end in ATE. There are more than this. I give my general chem kids a list of closer to 40 polyatomic ions, and you'll see when you get to a higher chem class, you might see more of these. But right now, we're just going to look at these 8. So, to write an ionic compound, we can boil it down to 3 simple steps. All right. First, you write the symbol and the positive oxidation number, symbol and positive charge for whatever the first word it is you see, that first element. All right. Unless you get ammonium, which is NH4 1+, the first word is a metal on the periodic table. If there's multiple charges, there should be a Roman numeral telling you which charge to use. So you write that positive part, that metal or ammonium. Second thing you do is you write the symbol and the negative oxidation number for the second word. Now there's a couple of things to keep in mind. All right, the first of which, if the word ends in "ide," you need to look for an element with a similar name because we changed the name to make it sound better. They named these things before they really knew what was going on. I just like to say we changed the name to make it sound better. So chloride, all right, comes from the element chlorine. Oxide comes from the element oxygen. All right, so if you see an "ide," except in one very special situation, if you see an "ide," it's coming from an element. All right, and then you use that periodic table from a few slides ago to determine what the charge is. If you see the word ending in ATE, or if that word is hydroxide, you have a polyatomic ion from the last slide. All right, and just keep the ion placed in parentheses. Don't forget to write the negative charge. And then you do what is my favorite part. You crisscross the numbers. You only crisscross the numbers. You don't worry about the positive and negative signs. You crisscross just the numbers because that tells you how many of each positive or negative charge will balance each other out. All right, we'll see some in the examples. And then if you can, reduce these numbers if possible. So if you have a 2 plus and a 2 minus, you would reduce the 2's to 1. If you have a 2 plus and a 4 minus, you would reduce the 2 to a 1 and the 4 to a 2. We'll see some examples of this as well. So let's look at these examples. We got some Reading ionic compound examples. We are going to start with aluminum oxide. And as we are starting with aluminum oxide, aluminum is Al. Aluminum has a 3 plus charge. Sometimes I write it as plus 3 because I screw up my pluses and minuses. It's not a big deal. Oxide ends in "ide." It comes from the element oxygen. All right, if I look oxygen up on that table from a few pages ago, I see oxygen's -2. Now I crisscross these numbers. The 3 goes down and becomes a subscript on the oxygen. The 2 goes down and becomes a subscript on the aluminum. I get Al2O3. What this means is I need 3 plus Als to balance out 3 2 minus oxygens. Right? The charges don't crisscross. Next one, sodium acetate. Sodium is my metal. Sodium has a charge of 1 plus. Nitrate ends in 8. It ending in 8 here means that it is a polyatomic ion from that chart of 8 polyatomic ions a few slides ago. So, make sure you have that readily available. Nitrate, as you can see from that slide, is NO3 with a 1 minus charge. So now we crisscross just the 1's. And if you have 1s as subscripts, you do not have to write them, so I get NaNO3. I like to keep my polyatomic ions in parentheses all the time, but if there's only one of them, you do not need to have it in parentheses. Third example is calcium carbonate. Calcium is my metal. It is Ca. It is in group 2 of the periodic table, so it has an oxidation number of 2 plus. Carbonate, once again, ending right here in 8, which means that it is a polyatomic ion from that table. In this case, carbonate is CO3 with 2 negative charges, so CO3 2 minus. I take those numbers, those 2's, not the signs, I crisscross them. And then since they're both 2's, what I do is I go and I reduce them to both be 1's. And I get CaCO3 as my answer. Again, I like to keep the polyatomic ions in parentheses to remember that I have them, but a lot of times you will not see those parentheses right here around a polyatomic ion if there's only one of them. My fourth example is magnesium phosphate. Magnesium is right near calcium on the periodic table in the same group, so it has the same oxidation number of 2 plus. Phosphate, again ending in 8, is a polyatomic ion. Phosphate is the only 3 minus polyatomic ion from that chart of 8 ions a few slides ago. It is PO4 with a 3 negative charge. So I got to crisscross these charges. The 2 goes to the PO4, the 3 goes to the phosphate, the 3 goes to the magnesium. I get Mg3PO4. I need the parentheses here because that 2 tells me I have 2 of everything in the parentheses. So 2 phosphates, 3 magnesiums. 5 and 6 both have Fe for iron. 5 is Fe plus, or Fe with a 2, which means it's a charge of 2 plus. This Roman numeral 2 means that it has a charge of 2 plus. Sulfide ends in "ide." It comes from sulfur. Sulfur has a 2 negative charge. It's right below oxygen. Crisscross, applesauce, those 2's. Those 2's can then be reduced. I get FeN. S. Number 6 also has iron and sulfide. It's a very similar compound, at least in terms of its name. If I look into number 6, iron, still Fe. Roman numeral 3 means the oxidation number or charge is 3 plus. Sulfide ends in ide. It comes from an element. The element that's like sulfide is sulfur. Once again, sulfur's symbol is S. Sulfur is in group 16, right below oxygen, which has a charge of 2 negative. And then what I do is I crisscross the 3 and that 2, and I end up with Fe2S3. So notice that Roman numeral makes a big difference in my answer on numbers 5 and 6. The opposite of writing an ionic compound is naming it. This is going the other way. We like to go both ways here in chemistry. And there are 3 steps also to naming the ionic compound. First, you write the name of the metal. All right? And I'm going to, you know what, add a little thing in here. Or ammonium. Which is NH4. 1 plus. All right. And then for the nonmetal, we have a little if-or statement here. All right. For a nonmetal or metal element, we change the ending to ide. We saw this in the other examples. Oxygen becomes oxide, chlorine becomes chloride. If there are more than 2 different elements in the entire compound, it must have a polyatomic ion. You just name the polyatomic ion. It gets super easy then. The hardest part of this comes with those special ions that have multiple charges. If the metal has multiple charges, you have to reverse the crisscross. The metal always has a positive charge. The non-metal or polyatomic ion always has the negative charge. It's the same every time. All right, and you have to do this to determine the charge of the metal, and we place it in Roman numerals after the name. So if I had iron with a +2 charge, I get iron Roman numeral 2. Iron with a +3 charge gets iron Roman numeral 3. We'll see some examples of this right now. So I was able to fit in the rules onto this slide, which is really nice. So I'm going to write some ionic compound examples. Li2S, well, Li is lithium. All right, don't worry about the 2, you just name the metal. It doesn't tell you to do anything with that number, so I just name it lithium. S is sulfur. All right, the element sulfur, but we got to change the ending. Remember, we don't like the sound of sulfur, so we change it to sulfide. And then I'm just going to rewrite it to make it look a little nicer, and I get lithium sulfide. Example 2, I have NH4 at the beginning in parentheses. Notice ammonium is going to be NH4 with a positive charge. All right, I have that NH4 in parentheses, so I'm starting out with the name ammonium. The second half of this is the Cl. Cl is a single element called chlorine. Once again, ammonium chlorine doesn't sound great, so I change the ending to ide, and it becomes chloride. And then all I have to do is rewrite it to make it look nice and pretty. And this would be rewritten as ammonium chloride. And by pretty, I mean that there's no like big X in it. I am not talking about my handwriting. I am sorry. I know it's bad. Example 3, we have K. K is everybody's favorite element to spell. That is potassium. Alright, it's everybody's favorite element because it has ASS in there, and that's always fun to write down. CO3 is in parentheses, alright, plus it contains more than one element, so this is a polyatomic ion. I need to go look it up. CO3 has the name of carbonate. I don't change the ending of polyatomics, so I'm done. The name of this is just potassium carbonate. See, polyatomic ions can make this really easy. Number 4, we have Ca. Yeah, there's 3 of them, but we're just worried about the symbol. Ca is calcium. PO4 is more than one element. It's a polyatomic. All right, yeah, there's 2 of them, but again, just got to look up what PO4 is. PO4 is polyatomic named phosphate. And this gets the simple element of calcium phosphate. Now in number 5 and 6, we're dealing with iron. Remember, iron was one of those 4 special ions we talked about several slides ago. But in each case, the Fe represents iron. So I named the metal, like the red step says. In the blue step, we have oxygen for both of these. And remember, we're going to change the name from oxygen to oxide. So in both these cases, oxygen becomes oxide. They're both iron oxides of some sort, but there's a difference. To tell the difference, I have to reverse the crisscrosses. So the 3 on the oxygen originally came from the iron, and that had to be positive. The 2 from the iron originally came from the oxygen, so it had to be negative. Since I have a charge of +3 or a charge of 3+, I get a Roman numeral 3. So Fe2O3, more commonly known as rust, is actually iron, Roman numeral 3, oxide. Number 6, this is one of the hardest ones of these you could ever do because there's a little hidden trick. If I reverse my crisscross, I get a 1+ for iron. I get a 1- for oxygen. The problem is if I go back earlier in this PowerPoint or earlier in this video and look at the different tables, I do not get a 1+ for iron and I do not get a 1- for oxygen. Oxygen, for our purposes, cannot equal 1-. It does not have that oxidation number. Its only choice, the only oxidation number it has, is 2-. All right, it is in group 16 if I go back to the periodic table page. So, because it's not showing me the 2- here, because it's acting like it's 1-, there must have been a reduction. Remember when we reduced things when we crisscrossed before? So that oxygen really should have been oxygen with a 2-, meaning the iron had to have a 2+ so that it would have canceled. This 2+ means that iron gets a Roman numeral 2, and so I have iron 2 oxide in the case of FeO, which is different than iron 3 oxide. All right. Examples like number 6 are the hardest, all right? But as you work through the homework that goes along with this set of notes, make sure you have those 3 pictures from earlier in the notes available somewhere, and also, make sure you use them. And then if you have questions, swinging by at a Flex or a Flex office hours or asking your teacher to explain something would not be the worst move in the world. All right. Again, if the only thing tricking you up at ones like number 6, that's not the worst thing ever. All right, guys. Take it easy. Have a good one.